And next up, we have Anya Nugent from CFA, who's going to be telling us about why host galaxies are so important.
Yeah, okay, everyone can hear me? Okay, cool. Hi, everybody. My name is Anya Nugent. I'm a postdoc at the CFA. And yeah, today I'll be telling you all about how we can use host galaxies in this upcoming big data era. All right, so I think as many of the talks have already highlighted so far, in the next year, we are going to be discovering far more transients than we can feasibly spectroscopically follow up or even analyze in real time. And many of us are wondering, how do we actually go about identifying the transients that we care about and building robust samples of those transients so that we can do the science that we're interested in, whether that's for cosmology studies or progenitor studies or whatever. And I strongly advocate for the usage of host galaxies to do both of these things. And this is because host galaxies have really been key in distinguishing transient types and identifying their progenitors. So one way we can see this is by looking at how different transient populations track star formation and stellar mass, which is what I'm showing in these plots over here. So up at the top, we're looking at 2D distributions of specific star formation rate and stellar mass for a variety of supernova populations. And down at the bottom, we have 1D distributions of those same properties. And as you can very clearly see, all of these different supernova populations trace a different combination of those two properties, which is intrinsically tied to their progenitors. So for one example, we see that type 1a supernova more regularly occur in more massive galaxies that have lower star formation rates. And that is due to their progenitor having longer formation timescales than that of core collapse supernova, which allows them to more regularly occur in more evolved galaxies. So another thing that we can look at is metallicities of galaxies. So in these plots over here, I'm highlighting several transient populations that have been connected to having young, massive stellar progenitors. And we can see that even though all of these transients are probably coming from massive stars, their host galaxy metallicities are very different. And this is because the mass of those massive stars is different and the metallicities of those massive stars are also different. So not only is this a way to better understand the progenitors of these transients, but this is also an identifiable feature of the transients that we can use to help identify them in the future. Now, because of that, host properties can be helpful in early transient classification. And indeed, host properties are used in some machine learning-based transient classifiers. So an obvious no-brainer of a really useful host property is their photometric redshifts. And this will help us better constrain transient luminosities and light curve width, which is going to greatly help in classification. But other host properties can also be useful, like their colors, star formation rates, stellar masses, like we just saw before. So there's a variety of papers that have explored those. I'm highlighting one in particular. This is Splash. Basically, Splash receives an alert of a transient. It determines a host galaxy for that transient. And then through getting optical photometry of that host galaxy, it infers a star formation rate and stellar mass, as well as a redshift. And then that, along with the offset of the transient from the host, it determines if that transient could be a type 1a supernova versus a core collapse supernova. And they had a lot of success in distinguishing between those different transient types. And so this is used without any photometric information of the transient itself. So this is a great way for us to think about how we might want to use something similar when we have very scarce photometric coverage for many transients detected in Rubin or Roman. So another thing that host galaxies give us is line of sight extinction. As I'm sure all of us are very aware, dust can have a massive effect on the colors of our transients. So for example, dust can severely redden transients, and this may make type 1a supernova, for example, appear more similar to type 1bc supernova. And in fact, we found evidence of this just by looking at host galaxies, where we were looking at properties of type 1bc spectroscopically classified supernova compared to a photometrically classified sample of type 1bc supernova. And we saw that many of our photometrically classified type 1bc supernova in very dusty galaxies actually looked like they had light curves that were more similar to type 1a supernova, meaning that they had probably been misclassified. So dust is something that we definitely want to be constraining to get the most accurate classifications on all of our transient populations. Okay, so now that we have a baseline for understanding why host galaxy properties are useful to understand, what tools are actually available to us to be able to determine host properties in this big data era? So as many people who have probably done host SED modeling are well aware, robustly inferring stellar population properties is often quite slow and computationally expensive. So I'm bringing up my stellar population property inference code of choice. This is called Prospector. And within Prospector, you're fitting your data with a nested sampling fitting routine to determine posterior distributions on all of your stellar population properties of interest. Now, within that routine, Prospector is making a ton of very expensive model calls, meaning that your fits can take up to 2 days running in parallel on a supercomputer to complete. So if we're thinking about the amount of galaxies that we're going to have in Rubin and Roman, that is way too much computational time for us to be using something like Prospector. So instead, we need to be shifting our attention towards maybe machine learning-based algorithms that can speed up this much faster. Okay, and luckily, there is something that can solve this computational complexity, and this is called simulation-based inference. So what is SBI? SBI essentially uses normalizing flows to learn posterior densities of our stellar population properties of interest directly from simulated photometry. So your training set is comprised of a set of stellar population properties and the simulated photometry that they refer to. So that when you're ready to fit your data, all you have to do is hand it your photometry and it will give you posterior distributions on all of your stellar population properties that you're interested in fitting. Now, SBI was used successfully in a paper led by Bingji Wang, where they were trying to do SED fitting of galaxies in a JWST survey. And what was cool about their model is that they added the ability for SBI to handle missing and noisy observations, which was not in the baseline SBI model. Now, obviously, this is really important because galaxies might be undetected in certain filters, or we might be missing data, or they might have more noisy photometry depending on the night that we get it from. And so that's going to be really useful for fitting a large populations of galaxies in the future. Now, another thing that they also found in this study was that the shape of the posterior distributions output from SBI++ seemed to match those from traditional nested sampling techniques. So you're getting those very robust posterior distributions that you would with traditional Prospector nested sampling, but in a much faster way. So we were really excited about this, and we wanted to see how useful something SBI++ would be in a rapid transient tool. So this is what we did in our tool called FrankenBlast, which if you are aware of the Blast web server, FrankenBlast is based on that. Basically, we took pieces apart of Blast to make this model and then put it back together, and that's why it's called FrankenBlast. So what does FrankenBlast actually do? So it gets a transient RA index and then does a host association with this code called Prost. I don't have a ton of time to talk about Prost today, but I highly recommend that we use Prost to do host galaxy associations. And I do think it works much better, especially for determining highly offset transient host galaxies than more traditional methods like probability of chance coincidence. So after the host association, FrankenBlast will do host aperture photometry using a ton of images from existing archival surveys, including Galaxies, DES, PanSTARRS, TUMAS, and WISE. And then after that, it uses the photometry and it does a host SED fit with SBI++. And the best part about all of this is that it does this in 15 minutes per object, which is way faster than Prospector does. And all of this can be run on your laptop. There's no parallel computing needed to run FrankenBlast. So going a little bit deeper into our SBI++ model. So this is trained on Prospector stellar population models, except once again, we're not using nested sampling. We're replacing that with SBI++. And noised up mock photometry from the surveys that I was just mentioning. So our training set, we basically use Prospector to build all the stellar population properties that we're interested in. And then we noise up photometry using SNR models from each of those surveys to make the photometry look more realistic to the ones that we will actually be fitting. Now, I will mention that that is the most important part of this model, because this is how we really understand the shape of those posterior distributions and how uncertain we are on all of our stellar population properties. And I will mention that we did have to update our SNR models from what BLAST did. Ours are a little bit better, so you should use our models. And if you're familiar with BLAST, we did make a few additional updates to the actual stellar population model that we were using. So for one, we have an expanded redshift range. BLAST only fits galaxies out to redshift 0.2. We fit galaxies out to redshift 1.5, which should be better for the transient host galaxies in Rubin that we'll soon be discovering. And then also we have allowed FrankenBlast to fit for photometric redshifts, which is also going to be great because we know that there'll be many host galaxies where we don't have previously determined spectroscopic or even photometric redshift estimates. Okay, so now taking a look at how well we did, what was really exciting is that we noticed that our SBI++ model provided better solutions and more accurate uncertainties than traditional prospector nested sampling. So just showing you an example of this with how well we were able to recover photometric redshifts. So prospector is shown in the red here, and you'll notice that in a lot of these cases, prospector has found a very incorrect photometric redshift, but also has very small uncertainties on all of those redshift estimates, which is terrible because that means it's really sure about something that's very incorrect. Now, meanwhile, SBI++ tends to have larger uncertainties, but they do capture the true redshift, which is great. And that's even better because that's going to affect our inferences on redshift-dependent parameters like stellar mass, which we can see in the next plot. And the reason for this is that oftentimes nested sampling gets stuck on local minima more often. And this is just not so much an issue in machine learning-based methods. So in addition to building FrankenBlast, we also tested it on 15,000 supernovae discovered by EZ and ZTF. So I'm showing you the breakdown of that supernova population below and our redshift distributions. And a lot of the plots that I was showing earlier in this talk were from this study. Something that I really quickly wanted to mention is that we did a comparison between spectroscopically classified supernova host galaxies and photometrically classified supernova hosts. And you'll notice here that photometrically classified supernova tend to occur at higher redshifts. Now that's important because this actually affects the distributions that we get for stellar mass and star formation rate, redshift dependent parameters, as these do evolve as a function of redshift. And so I do think that host properties are going to be really important for us to use in the era of Rubin and Roman, but something that I really want us to be aware of is that these populations are going to be existing at much higher redshifts, so we have to be smart about how we're using the host properties in that time. And then finally, I just wanted to pull up this plot that Ori showed yesterday. So this is just another photometric redshift code called EASY, where I tested it on simulated photometry from LSST and Roman. And I really wanted to highlight this to show that using broadband optical to near infrared photometry is the best way for us to infer photometric redshifts. And so I think we really need to be thinking about how to combine data from Rubin, Euclid, and Roman to get the best inferences on these properties. And then I have tons of FrankenBlast models available. I have things available for LSST and Roman, and I really want to hear from you about what's most useful for you. So please, let's chat more. Thank you very much.
Okay, we have time for a couple of questions for Anya. Yep, Sam.
Thank you. That was a great talk. I was wondering about your thoughts about, so sometimes the local environment of the transient is not represented by the global properties of the host galaxies. And I assume in a lot of your modeling, that's just having the global properties of the host. What are your thoughts about this?
Yeah, so we actually did not do any local environmental analysis. BLAST does, but I think it's very redshift dependent, and it depends on the angular size of the galaxy, how well they're able to infer local environmental properties. I don't think that that's going to be possible for a lot of the hosts that we will have with Rubin and Roman data, just because I'm expecting them to be at higher redshift where angular resolution is going to be quite minimal, and it's going to be more difficult to get local properties. But maybe something exciting to propose for an HST data or JWST data.
Gautam?
Hey, Anya, great talk. So obviously in Sima, we're very excited to see FrankenBlast and ready and waiting to upgrade Blast with this. But one thing that still strikes me with using prospector models is, we keep learning from JWST that galaxies at higher redshift are significantly different than many of the models we've seen. And there's enough evolution, particularly morphologically, but also with major mergers, et cetera, that none of these simple models might be a good fit for things at high redshift. So when we move to high redshift Rubin and Roman data, what are your thoughts for how we can use real data with maybe domain adaptation or whatever to improve our constraints on things like specific star formation rate at the really highest redshifts?
Oh my gosh, it's a loaded question. I mean, I think we can only do as well as our model has, but I think staying updated with the Galaxy community and how they're continuing to improve their models, which there are several adaptations to Prospector, which take into account that we're discovering many more high mass galaxies at higher redshift. And so I think continuing to update what we're doing and incorporating those models so that we can get the best inferences on all of our stellar population properties is the best way to do it.
So let's thank Anya again.